related to this particular setup. A heavy rod, a string which is attached to one end of this rod and keeps it horizontal. The questions are about the same force. Well, let's make it the exact copy of the picture. Here. The string, the rod, the force of tension clearly is acting on this rod because if we cut it, it wouldn't be horizontal, it would fall. And as we remember from yesterday, the direction of a torque depends on the choice of the axis relative to certain axis. The direction might look differently, and everything which acts or moves counterclockwise we call positive, and everything which acts or moves clockwise we call negative. So, and while I'm waiting, because two questions, so it takes a little bit more time than one question to answer. So, again, torque is not just about opening and closing doors, right? Every time when we need to rotate things to make them spin, we use torque. If we need to use a wrench, we use torque we have to apply. And when you hold the wrench so very close, you can feel it's harder to rotate the bolt or wherever it is. That's why people hold the wrench at the edge. And if you need a device which spins, you have to generate torque. And here, I'm glad you came. I was waiting for you. Yeah. Here we have a device which helps to feel the torque. You know, some feelings actually are good to experience. Feelings which comes from physics. So if you hold this, you can feel how strong should you apply the force to the handle to keep this horizontal, right? But your feeling will change with every additional centimeters, right? See, I knew he's strong, but even he will give up soon. Not yet?
I got sweaty hands.
All right.
You're gonna fall. There you go.
Here goes. So a very simple experiment. I usually keep it here for everyone who want to try it. You can feel how torque changes with the distance. The force of gravity acting on this weight is the same. I just shift it. But as long as I move it away from the physical axis of rotation, it generates stronger and stronger torque. So to prevent it from rotating, he had to apply stronger and stronger torque, and eventually it wasn't possible. Actually, the force responsible for that torque is a force of static friction, which always has a limit. So when that limit is reached, that's it. All right, let's see what's happening to the Weber sign. As long as it works, that's fine. So, perfect. Well, let's do it. Thank you for letting me know. So, how many forces are acting on this rod? How many forces do act on this rod? Three. You can see two, and there is of course the third. Touching means interacting. Interacting means a force. So this is just a picture. We want to convert a picture into Freebody diagram, so we have to show all the forces, and one more force should be acting here. Now, what do you think is the direction of that force? How does it act? Would it be just vertical? Would it be just horizontal? We know that in equilibrium, the sum of all forces must be equal to 0. All forces have to cancel each other. The net force has to be equal to 0. The sum of all forces has to be equal to 0. So this one force, which is so far missing, should cancel both force, gravity and the tension. So it should point something like this. We don't know exact angle, but okay. Now, the next step, I'm just going through the steps of the reasoning. The next step is choosing the axis of rotation. Well, in the questions, the axis of rotation, question 2 was about left end of the rod, which is hinge, and the right. So let's just go. We have 3 forces and we have 3 natural points to choose the axis. So let's just do all of them one by one to practice in seeing the sign of a torque. So first I want to choose the axis here. And people use O origin to indicate the axis, or A axis, whatever it is. Relative to this axis, hinge, left end of the rod, this force of tension, axis, tension, it should be straight. This force of tension generates torque, which is, what did you say? Positive or negative or 0? These are only options. Well, it is positive. Now, there is a standard, like a procedure, which helps us to see. And that procedure is, first of all, I always recommend redraw the picture, at least at the beginning. Just keep the axis and the force. So don't look at anything else. There is axis and the force. Anything else is irrelevant for this question. Now, you can extend the force vector. This line has a name, line of action. Now, you can bend ends of this line toward the axis. So that would look like a small part of a large circle with this axis all inside it. And now if we look at it from above, what we see is point and something like that. So this line has no name, just helpful. It has this point inside, and the direction is provided due to force. And now if we look at it, we can see this direction has a name, counterclockwise. As long as you said the name, after that, you just apply a definition. Counterclockwise means positive. So the torque, the force of tension relative to this axis, is positive. Well, what about same axis but different force? Same axis, but gravity. The torque due to force of gravity relative to this axis. And again, when we say torque, we mean the z component, the component relative to this axis, which points out of the screen toward us. And again, because it's a number, as any number, it might be positive, 0, or negative. That's it, only 3 options. So what do you think? Gravity, axis, the torque, positive or negative, or 0? Negative. So if you see it clearly, good. If you still kind of think how to see it, well, repeat the procedure. First, extend. Weird. The only color I have today is red. Interesting. What about eraser? Eraser works. Red. Okay, so today the only color will be red. Anyway, so extend the force in both directions and then bend. Well, how? Imagine that you're making a circle with this point O inside it, so you should bend it toward it. And now you can kind of see the direction. You just imagine that you look at it from afar, and this direction has a special name. We call it clockwise. And after we said these words, clockwise, or one word, clockwise, we know what it means. It means negative. So this torque of this force relative to this axis is negative. Well, and well, keep the same axis. Last force. This force has no name. We can call it contact force, actually, due to a contact. This is the axis. And again, torque of this force relative to this axis, we have to make a choice. Positive, 0, or negative. These are only the choices. So, what do you think? Wrong. What do you think?
Positive.
Wrong. What do you think?
0.
You're right. That's how we do it on the exam, right? You got to draw a line. Now, this line goes through the axis. You have no idea how to bend it. No matter how you bend it, it's not going to be a circle. There is no direction, neither clockwise nor counterclockwise. But more importantly, this is a case when we actually can apply that equation we wrote one time yesterday for the magnitude of the torque. It should be equal to the product of two numbers. One number should be equal to the distance from the axis to the line of action. So do you see any distance between this dot and this line? No, there is no distance. So we also can ask, does this vector has a component perpendicular to this line? No, because this vector actually lies on this line. So here we're actually multiplying 2 zeros. 1 0 would be enough already, but here we have 2. So, well, of course, now we got to move on to practice to the next natural location of the axis. The next natural location of the axis is here, and you have 3 pictures to draw right now. Hinge, contact force, axis, torque of this force relative to this axis. Then move on to the next force, axis, gravity, torque of this force relative to this axis. Finally, axis tension. And you should say something about torque of this force relative to this axis. And every time you just have to choose between three symbols: greater than 0, equal to 0, or less than 0. Well, we don't need this anymore. So the contact force. What do you think? Negative. Yep. Again, we don't have to draw it every time, but this is still what we're imagining. How would it make it spin if nothing else would be acting on it? If nothing else would be acting on it, only this force, the direction is clockwise, and that means we have to erase or cross these. Should be negative. What about gravity? 0. Yep. When a force, well, aims exactly at the axis, there is no arc, there is no distance from the line of the action to the point, so 0. And what about tension? Yes?
So why gravity should be a constant force all along like the rod, right?
Yeah. The gravity is acting on each individual part of this object. So what we do, we imagine many tiny parts of it. There's a tiny force of gravity acting on this, and this, and this, and this, and this, and this. We add them up all together. We get one force of gravity, and we apply it to the center of mass. And for any uniform object with uniform density, force of gravity applied to the center of mass, and center of mass is always at the center in the middle. And maybe I will prove it later on, maybe not. There is a slide with this statement in the future. So this is the force of gravity acting overall on this object. This is the center of mass of it. And tension generates torque relative to this axis, which is
It's positive.
positive, because, again, if we look at how would this rod move if only tension would be acting, it would be spinning counterclockwise, and counterclockwise means it should be positive. Well, one more axis here. Let's start from the torque due to tension. That was question 3. Tension, axis, torque of this force relative to this axis, 0. Same force, different axis, different answer. That's why it's very important to choose the axis and stick to this choice. Now, what about gravity relative to this axis? This is direction we call counterclockwise. Torque of gravity relative to this axis will be positive contact force. Now, what people sometimes do, they kind of start drawing this line which represents the possible action, and they do it like this. What's wrong with this? They leave the axis outside. The axis is supposed to be inside because we want to kind of spin about it. So, and that is the direction we call clockwise, and that means this torque relative to this axis will be negative. That's very important. A question. So, remember in the past we said something similar about velocity. Velocity is a shortcut. The full name is velocity of this object relative to this reference frame. Same is true about torque. When we say this word torque, it is only a shortcut. The full name is the torque of this force relative to this axis. And when you say this word torque, you need to be able to say the whole sentence from the beginning to the end. What axis? The axis of your choice. Where can you choose the axis? Anywhere you like. And these are the answers for questions 2 and 3. Now, this was the slide we wanted to finish. Let's do it very, very quickly. So, the axis for all 4 situations supposed to be at the hinge, and case A, the magnitude of the torque should be equal to this distance. What is happening today with my system? Which is 0.9 times the y component of this force. The y component is that component which is perpendicular to the line which connects axis of rotation and a point of application. And this is just 5. .5. What should we write? Well, the equation tells us that the unit of a torque should be a product of 2 units, a meter from the distance and a Newton from the force. And we've seen this unit before, and we called it joule. Now we don't call it joule. Now we just keep meters times a Newton, meter times a Newton. Here, B. Okay. This is the distance. So 0.9 over 3, 1/3 of the times same magnitude. So 4.5 divided by 3, 1.5 a meter times a Newton. Well, angle, C. Axis of rotation, point of application, that's R. So same R. Times. Well, now we need to find the component first. How do we find the components? Well, we use a triangle. This little thing is supposed to be used for calculating torque, but we know this angle is 10 degrees, and so the side we're looking for is opposite to the angle. Opposite means use a sine. So instead of 5, we use 5 times sine of 10 degrees, wherever it is. D. Point of application of the force, axis of rotation, that is distance, which is 1/3. How do I know it's 1/3? Because I read here in cases B and D, the force is applied 2/3 away from the end. So it means this part should be equal to 2/3, so what's left is 1/3. And again, it's going to be sometimes I really wish I wouldn't have any Russian speaker people in the class. In that case, I could swear. Now I have to bottle my feelings inside me. So 5 times, well, the y component is the same. Again, wherever it is. You can tell me the numbers, last two numbers, please, so I would finish.
0.78 meter-newtons.
Thank you. All right, any questions? Now let's quickly repeat the same calculation relative to a different axis. So while I'm going to be doing calculations, you should be answering that question. That question is about the last case, D. Torque of this force relative to, well, the axis is here now. In reality, in the real life, of course, the doorknob is a little off the edge. We neglect that. Yeah. So we have 4 cases. Case A, torque will be equal to, and what number should I write for the distance in this case? This is the equation. Distance from the line of action to the axis. 0, there is no distance, so 0 times whatever force is equal to 0. Case B, here, the magnitude of this torque will be equal to, well, now distance R is equal to 2/3 of the total distance. But the force has still same magnitude and still perpendicular. So I'm still waiting for your answers. I'm doing C, axis, axis is, axis, the same. Case C, torque equals, please, number? 0. No distance again. 0 times wherever it is, still 0. And case D, it's about direction. We didn't say anything about directions in this situation. So let's review quickly. No direction because 0. Counterclockwise positive. counterclockwise positive, counterclockwise positive, and here 0, no direction. Here clockwise negative, 0, no directions. We've got all possible answers. Well, again, this is a case when I recommend just help yourself to actually draw only two elements, the axis and the force. That's how the force aims. But now, if you extend this force and bend it, that will represent the direction which we call clockwise. And clockwise means this torque actually should be negative. And the magnitude of this torque should be equal to, I don't know yet. I need to calculate. This is the R, which again 2/3 of and now we need to multiply by the same Fy. So it's going to be 5 times sine 10. And please tell me again. 0.52. Any questions? This is very important to to practice, because after that, we're going to make a leap. First of all, geometry. As you have seen just 5 minutes ago, we've been using geometry, right triangles, for calculating this component. We can do it in general. So we can apply the same geometry to this triangle. This component will be equal to product of hypotenuse times sine of this angle. So this is an expression which we always can use to calculate the magnitude of any torque for any force. Which do you want to use? Well, now it's up to you. There's an original expression, which kind of more physical. There's next expression, which is a geometry. Turns out there's one more, the third one, which also comes from geometry, but geometry involving not forces, distances. So the axis of rotation, the point of application of the force. This is the force. If we extend the force, we get a line. That line has a name, line of action of this force. If we draw a perpendicular from the axis of rotation toward the line, that perpendicular has a name. Well, different people pronounce this differently. In Britain, they say lever arm. In the US, lever arm. Call wherever you want. If you look at this picture, because of a way it's been drawn at 90 degrees, this line represents the shortest distance from the axis of rotation to the line of action. Any other line will be longer than this one, longer. So this is an official definition of a lever arm. Shortest distance. It should represent the shortest distance from the axis of rotation to the line of action. Now we can take a look at this large triangle. In this large triangle, R represents the hypotenuse. And the lever arm is opposite to the same angle. So we can rewrite the expression. We can keep the force, the actual magnitude of the force, but this product, hypotenuse times sine of the angle, is equal to the lever arm. That's it. So we have 3 ways to calculate the same torque. 3. Which do you want to use is up to you. I prefer the last one because Archimedes preferred the last one, and I'm with him on that. But now we can make a next step in our reasoning. If several forces acting, each force generates its own torque. Some torque might be positive, some might be negative, some might be 0. If we add all together, we call it net or total. How does net torque affect an object? Well, that depends. This is what the net torque is. We, of course, only use the components relative to the axis of rotation of our choice. It's very important to use our imagination to see those forces, because if we look like a top view from above, some of those forces are responsible for positive torques, and some will be responsible for negative torques. We need to see those positive and negative torques, because if we make a mistake, the net torque will be wrong. And what does the net torque do? Well, this is not a Web assigned question, right? This is not a tricky question also. What do you think will be happening? This is a very important experiment. I want to do it. I need a rod, and I need to apply 2 forces to it, which are, first, equal in magnitude, second, opposite in direction, and third, applied to the same point. How can I do that? Watch carefully. Watch and learn. See? So what did you see? Can you describe what was happening in words? You can use your own native language if you're not an English speaker. I don't care. But it's very important to be able to describe what's happening in your own words. So was it rotating? Not at all. How do we call this? Equilibrium. When an object was initially at rest, and then we applying forces and torques, but net torque is 0 and net force is 0, the object remains at rest. That's what we call an equilibrium. And it doesn't have to be 2. Could have been more forces, 3, 4, 10, doesn't matter, if we account for each force, if we account for each torque, if net force is 0, if net torque is 0, and if the object was at rest, it remains at rest. That's it. So equilibrium, this word now means 2 things. First, it still means net force equals 0, like it was before. But in addition, when we talk about large objects, not just about a ball, it also means net torque equals 0. So now we extended the meaning of this word equilibrium to a large object. If something is in equilibrium, it means net force equals 0, net torque is also equal to 0. That's it. Not equilibrium. Well, I give away the answer here. All right, but still, it's a very important experiment. I want to do it. Years of practice. You need to apply 2 forces which are same in magnitude, opposite in direction, but applied to different locations. So net torque would not be equal to 0. So now it's imprinted for the rest of your life in your memory. Net force is equal to 0 in this experiment. Forces opposite in direction have same magnitude, they cancel each other out, but net torque is not 0. And this results in spinning, not just in spinning with acceleration. Angular velocity was 0, then it was not 0 anymore, so change in the velocity means acceleration is not 0. Now, torque, kind of tricky thing, because how do I say torque is 0 if I don't say anything about axis? Well, in this experiment, again, we know we can choose axis anywhere. If I choose it here, clearly each torque is 0, so net torque is 0, and if net torque is 0 relative to one axis, it will be 0 relative to any axis. You can choose the axis anywhere, calculate net torque, it's still going to be 0. Here, well, here, same thing. Let's choose it here. Torque due to central force is 0. Positive torque, negative torque, cancel each other out, net torque is 0. Here, I can choose axis here. This force has no torque, so that force gives net torque. I can choose it here. Now that force has no torque, but this force will give the net torque. I can choose it here. So when an object is not in equilibrium, net torque is responsible for the angular acceleration. Remember, net force is responsible for the linear acceleration. That law we call Newton's second law. So this law we also call Newton's second law, but we say Newton's second law for rotational motion. Now, rotation is a more complicated motion. That is the coefficient between net torque and acceleration. Depends on two variables, on mass and shape. This coefficient, and I'm going to talk about it later in more details, but this coefficient is different for different objects. It has a name, a moment of inertia or rotational inertia. People call it differently. But it depends on the shape. If you see a ring or a hollow cylinder, well, assume the axis goes through the center. Because if we shift the axis, it changes things a little bit. But the moment of inertia is equal to this. If you see a solid cylinder and the axis goes through the center of mass like this and it spins like this, so this is for this guy. Yeah, one half. One half is for this guy. Sorry. Still sleeping. For this guy, no half, just mr squared. Where is it? Yeah, here. Hollow cylinder, mr squared. Sphere. Well, these are three most common objects. This one, and this one. For the sphere, the coefficient is 2/5 mass times radius squared. And we can spin a rod. 1/12. The coefficient is 1/12 mass times length. If you look at all these equations, they all have the same structure, some kind of a number, total mass, and size squared. This is only important when we need to calculate a specific number for something, for net torque. If we just talk about, how does net torque affect the motion, well, this is how. When net torque is not 0, the angular acceleration is not 0. If angular acceleration is not 0, the object is speeding up or slowing down. Now, if net torque is 0, we said that there is no acceleration. And if the object was at rest, it remains at rest. We call it equilibrium. And in equilibrium now, we can use Well, in general, we can use 3 equations. Net force, in general, might have 2 components, x and y. And net torque has a component relative to z-axis. So in general, for any solid object in equilibrium, we can write at least 3 equations. And I said at least, because for this equation, we can choose the axis somewhere else. We can choose it at one end of a rod, then we can choose it at another end. And we can use this equation many times. So for any solid object in equilibrium, we can write so many equations as we want to. Now, I'm finishing theoretical part. After that, we're going to do examples. This is the equation, the general equation for the net torque for the object in equilibrium. Net torque equals 0. What does it mean? The z component of the first plus z component of the second equals 0. These numbers, depending on direction, positive or negative. So if you have to remember, because different textbooks do it differently. If you use this equation, plus equals 0, each variable represents a component, which means it could be positive, negative, or 0. And another approach is using magnitudes. For a positive component of a torque, because it's a positive number, there is no difference between component and magnitude. But if components are negative, for a negative number, the component is equal to -1 times the magnitude. For example, -2, what is it? It's -1 times 2. So people rewrite this equation using magnitudes. But if they use magnitudes, for each clockwise torque, you should write a minus. So you're adding positive magnitudes, you're subtracting negative magnitudes, and they should cancel each other out. Or people balance it like this. On one side, you add all positive magnitudes. On another side, you add all magnitudes of the clockwise torques, and they should balance each other out. And that's why this law has a name, balanced equation, torque balanced equation, TBE. And that's why the equation for the force, people also call force balanced equation, FBE. So, well, this is the strategy which we've used if we need to solve a problem on the equilibrium. We have to draw a picture, we need to draw a Freebody diagram, then we have to choose the axis, then for each torque we have to make a statement, is it positive or negative? For each torque we need to write the magnitude, then we have to calculate that net torque, make it equal to 0. If needed, we have to repeat the same procedure for a different axis. If needed, we can apply the force balance equation. Eventually, algebra will give the answer. And now, you can do almost all problems from this homework. Almost. We still got to talk about angular momentum and rolling, but those things are easy. Any questions? Please. How could people live without coffee? Yes.
For the TBE, what is the torque Z? How do you calculate that?
Z represents the Z component, the component relative to which we observe in our mind the actual or potential motion of an object. this rod is in equilibrium. It means net force acting on it is equal to 0. It means net torque acting on it is equal to 0. But what we do when we look at it, it's not the diagram we want to use. To draw a diagram, we need to, well, first we need to draw the forces. And here, again, 1, 2, 3 forces. Then we have to choose the axis. And the axis of rotation has to be perpendicular to the forces. In our case, that's the only situation. We don't talk about three-dimensional stuff. So if your forces belong to the vertical plane, to the vertical surface, your axis, z, has to be perpendicular to it. And if it's perpendicular, you don't actually see it. This is how it looks. What you see is just the tip of this axis. So you have to imagine or even better, draw all those forces. And Z represents the actual value or the component of a torque of that specific force relative to you if you look in such a way. So Z axis tries to poke you in the eye. So this is a component of a vector. And I didn't mention it today, but we also have a right-hand rule, which actually represents that particular vector we call torque. For example, here, if this force, if I try to use right-hand rule, well, I'm kind of imagining I'm looking from above, yeah, but this is how would I do it. My fingers should demonstrate the rotational effect of that force. This thumb tells me that the torque of this force should point up, and relative to this axis, the component will be positive. And here, let's go back for the moment. Here, these symbols. They represent a vector, that actual torque, which points either out of the screen toward you or into the screen away from you. And relative to the axis, which always points at you, this vector always has a positive component, and this vector always has a negative component. All right. Well, it all comes clearer and clearer with more and more problems solved. Archimedes was the guy who heavily studied and heavily used mechanisms, mechanical devices based on mechanical advantage. That, well, we don't know for sure, but people say that's what he said once. Give me a lever long enough and a fulcrum, and I can move the world. Well, this is a very simple example how we can use a lever for our advantage. So this is the strategy. In this strategy, of course, all we have to do is just draw a diagram. This is the lever and lever. In this situation, we assume it's massless. A fulcrum, a support, a pivot, call it any way you like. So a person is capable of moving weight up to 60 pounds. 27 kilograms. We can use pounds, actually. It doesn't really matter in this situation. And turns out it's not enough to move a heavy rock. So the question is, if he would use this particular device, what mass could he move? Well, this is the force he can apply, 60 pounds. And this is the force he can compensate using the longer arm of the lever. Theoretically, again, in general, we would have to add two more forces. They theoretically should be force of gravity acting on this rod or lever, wherever it is, and of course the fulcrum. This force normally has a name, normal force. That would be mg, but we neglect this. And what do we do about this? Well, now there's a rule of thumb, which is very convenient. We choose the axis of rotation at the point of application of the force, which we don't care about. This force, normal force, is not zero. But if my axis is here, the torque of that force becomes zero. So I'm not eliminating force. I can't do that. But by choosing the axis at the convenient location, I eliminate the torque of that force. So what's left is just one torque due to this and one torque due to that. One is negative, one is positive. Which is which? Well, this force tries to spin it counterclockwise, and the force we're applying tries to spin it clockwise. So they should balance each other out, not forces. To balance forces, okay, let's write it. Force balance equation. What should I write? I should write mg plus 60 pounds down should cancel normal force. That's what I should write. But if I want to write torque balance equation, I need this L1, L2 distances. Now I can write torque number 1 has the same magnitude as torque number 2. Or I could write the z component of the first torque plus the z component of the second torque together should be equal to 0. These two equations are mathematically equivalent. So how do I use this equation? Well, literally, torque number 1, the one on the left, it should be equal to m times g times this. And the magnitude of the torque on the right should be equal to 60 times this. Now, I actually don't really need mass. I want to calculate weight. 60 times L2 over L1. If we use original units, 60 pounds, 150 centimeters, 30 centimeters, centimeters and centimeters getting canceled. That's also kind of convenient rule of thumb to remember. When we write the torque balance equation, we can use any unit for distance because that unit will be canceled as long as we use the same unit for all distances. So 150 over 30 is 5, 60 times 5. So this is the weight we can move with the use of this mechanical device. Without this device, the maximum weight we can move was 60 pounds. Now we can move 300 pounds. When Archimedes realized, he built very, very powerful machines and become famous. But then he was killed. Yes? That's not the work. What is that? In this situation, this W is what? Weight. Well, let's see if I can make something like this. For you, there's a question to answer. I'm going to use this time. I will try to assemble something similar, not exactly the same, but similar. Well, in the problem it says a meter stick. In the lab you will be using meter sticks. This is just a rod, it doesn't really matter. And actually I forgot, I need well, actually, first of all, it doesn't have to be a weight. We can actually measure what force should be attached to balance it out. This is a physical axis of rotation. This will be the lever arm for this force. Force of gravity is acting on this rod, and it is applied to the middle point, to the center of mass, which is in the middle. So how many forces are acting on it? 3. 1, 2, 3. Touching means interacting. But again, if we choose the axis here, only 2 torques in this situation will be important. In this situation, instead of a force, we have a weight. What the reading was? Because if I know the force, I can calculate the mass which I need to attach to it. What is the reading? About 4, right? 4 newtons. So the mass should be about 400 grams. Let's see. I'm deflecting your attention from the question. And you should not be deflecting your attention from the question. That's 300 grams. Close enough. 450. Let's see. Almost perfect. That is never almost perfect. But that's how it works. Now, what's the question? Gravity generates torque, which is, let's see what you said. What did you say? Well, you should have said something, right? So what was that? What do you do? Clockwise relative to what? Well, what if you assumed wrong? So what should you do in a situation like that? if you have to make an assumption, that means something is not clear. And if something is not clear, what should we do? Ask a question until it becomes clear. So you have to ask a question, well, Mr. V, relative to what? Because if you don't tell us relative to what, we can't answer this question. If we can't answer this question, it means no way, right? So this is a situation when I finally tricked you. You cannot answer this question directly until you get an additional information about which axis. Well, of course, natural choice is here, and relative to this axis, of course. Now everything is clear. Yeah. So let's just do it one more time very quickly. If we choose the axis here, which is the best choice because, well, this force, tension, or normal, this force is not zero. Again, the force is not zero here. But by choosing the axis at the point where force is acting, we're making torque of that force to be zero. And what's good about zeros? They're easy to deal with. The more zeros, the better. So in here we have one more force with not zero torque. And, well, in my problem, we have distances. Now, what is this distance equal to, please? Anyone? Distance from here to here. How do you know? We have to be able to prove every statement we make about every number, because if we can't prove it, we can't rely on it. And this is a case when geometry is important. There's information. What does this mean? This. It is 1 meter long. That's what it means. From here to here. Now, as we said, for a uniform object, force of gravity is applied to the center of mass, which is, well, for any object, force of gravity is applied to the center of mass. But for the uniform, it's actually at its physical center. So distance from here to here should be equal to what? 1/2 meter. And almost every problem related to torque involves some geometrical type of reasoning when we need to look at the sizes, distances, and relate them. Keep that in mind. In this situation, we use this information that it's 1 meter long. We use information that force of gravity is applied to the center of mass, which is in the middle at the center. That gives distance 1/2. 1/2 minus 30. 20. This type of reasoning is not related to physics at all, but it is a part of a problem-solving thinking. But now, of course, everything is very, very simple. Again, we only have 2 torques to balance out. Let's call them 1, 2. So I'm using magnitude equals magnitude. And here, 100 grams times G times 20 centimeters on this side should be equal to the mass of the meter stick times G times 20 centimeters again. So what can we cancel? Units, centimeters and centimeters, G here and here. What's left? The mass of this meter stick should be equal to 100 grams. Of course, next step is using more forces. So these are types of the problems which, from a point of view of how we solve it, how we reason through those problems, absolutely identical. There is no difference if we talk about a person walking on the board or exercising or a person on the scales, like here. The strategy is always the same. Freebody diagram, forces, axes, torques. Now, it's also very good illustration. Well, first of all, a meter stick. It's almost massless, so we don't see practically any difference here. What's going to happen if I place a weight? I can place it right in the middle. Well, I'll try. And we can see the forces should be equal to each other. What's going to happen if I move it? You can see the difference. Why? Well, because now it's not just about forces, it's also about the torque. And of course, if I know the exact location of this weight, I can calculate, I can calculate these forces. And then I can compare if my mathematics agrees with physics, and that's how we know it works. And if a person actually walks, this is the person. Eventually, as you saw, there's a critical location. He can't pass, because otherwise it starts rotating, it tilts. When does it happen? Well, it happens when this force becomes zero, because this board doesn't touch it anymore. And if you move just a little bit more, that's it. Now, in reality, of course, it might have some mass. So depending on the situation, let's say this is a problem we need to solve. How many forces do act on this board? The board is in equilibrium. Normal force number one, normal force number two. There is force of gravity applied to the middle point of this board, and there is a force due to this weight. How many torques? That actually depends. We can choose the axis. So what would be the most convenient choice? Well, we have 4 natural choices. Here, at the center of mass, at the location of this object, or here. And normally I would start from choosing here or here. To get rid of torque, do it in normal forces. And then we'll see how it plays out. So this is a problem, one of many, which can be solved with a straightforward application of the torque balance equation. I'm going to start solving the problem, and you should answer this question. That's the last question for today. What is the direction of force acting on the board from the bolt? That's the board. That's the bolt. To figure out the direction of the force, you have to imagine what would be happening without the bolt if you cut it. And the bolt prevents that from happening. And of course, we need the diagram, the board, the pivot or fulcrum. Now, this lady for us is just a source of a force of gravity. Sometimes anybody is just a source of a force of gravity. So her weight is 530 newtons. There is a force of gravity acting on the board, which is equal to 12 times 10, which is 120 newtons. There is a normal force acting here from the fulcrum, and we do not know that force. And finally, there is a force. Touching means interacting. So, by now, you should have entered your answer. How does that force point? What do you think? Down. It holds it. So, the force of the bolt. Now, where do you want to choose the axis of rotation? Well, the answer is don't choose the axis at the known force. Because you know it, you can use it. Choose the axis at the unknown force. So we have two natural choices, here or there. Let's choose it here. Relative to this axis, we have one counterclockwise torque and two clockwise torques. So we can balance torques immediately using magnitudes. Counterclockwise torque, do it a normal force. Normal force, we don't know it. If we don't know a number, we write a letter which represents that number, times distance from the axis, lever arm, 1.4. And that should be balanced out by, well, force 120 newtons times this distance. So this distance, this has to be equal to a half of the length of the board, 1/2 times 3.9, and we need to subtract 1.4, so it's 1/2 times 3.9 minus 1.4 plus the magnitude of another clockwise torque. And oh, sorry, I know I don't have time left, so that's why I'm rushing. And I make a mistake. Don't do what I did. Forget it. Please erase it from the tape. What mistake did I make? Very common mistake, almost everybody does sometimes. I switch the axis. I have to stick to my choice. So this should be the distance I have to use. Force is 120, and distance should be equal to a half of the board. Plus, and now, same axis, distance is the total length of the board. And that means I have 1 more minute left. And that means I'm going to use that minute today to write an equation for relative to the second axis, relative to this axis, counterclockwise, clockwise. Times 1.4, counterclockwise should be equal to 120 times. Now that should be 1/2 of 3.9 minus 1.4 plus 530 times times this distance. This distance should be equal to length of the board minus 1.4. Done. All right, that's exactly 10 minutes before 10. Well, I'm going to do more examples tomorrow, and we're going to talk about dynamics and stuff. So first of all, we are looking for the forces. So that's what we were looking for. And the equation we always use is torque balance equation. The magnitude of one counterclockwise